About what a rooted node tree is and what a graph data structure is while I'm rebuilding this one that we need. It's already been working. I already tested it and everything. I just need to port it over to the new PEGN architecture. And so I thought I'd start by actually kind of making this. I mean, this is work I need to do, but I also thought I could just go ahead and describe it a little bit. So let's start with the book Intro to Algorithms, which you might know. This is a famous book. It's usually the textbook in most data structures and algorithms computer science classes I've learned. And it's overly academic, the kind of thing that kind of annoys me. But there is a section on here on elementary data structures in chapter 10. And it talks about what a rooted tree is. So a rooted tree is a form of a graph. A graph is a data structure where you have nodes that connect. In fact, let's go see if we can find some more stuff on this. What is a graph data structure? And you'll know it's just a network. It's like, think of neurons, right? That's really all it is. And so yeah, I mean, I don't know how much graphics are on this one. I've never been here, but a graph data structure, right? So it's just, you got nodes and you got connections between those nodes, and there's all kinds of amazing weird things you can do with that. If you go to any web page and just inspect element, this is our quantum stuff, you can see a number of you can see the DOM. If you go to the inspector, let me see if I can find one. Well, you can't really see it right here right now, but so the DOM, the document object model underlying all web pages, is a node tree. And all these are children. You have a top level node. The top level node is a document, and then you have subnodes under that. And these nodes sometimes correspond to elements, and sometimes they don't. Hi, silly. And so yeah, this is a very, very common thing. The internet itself is a graph model, and but then I learned. And by the way, I have no formal training in this. This is just all from my own reading and study. And so yeah, when I go to look at what we have here, we have this in this book, Intro to Algorithms. We have what's called a rooted node tree, methods for representing lists. And so this is a linked list. So it's kind of builds on the idea of a linked list, which is another data structure. And the linked list, you have things that kind of like link from one to another. So you have this connector that goes to this thing, and this connector that goes to this thing. So it's like connects them all together, and you can move things around. And this kind of data structure is really essential. It's built into any language you use that has the idea of a list or an array in it. It usually has this kind of stuff underlying inside of it, including slices and Go. And so then when you go to look at to look at it the next level. So what if we add another dimension, right? Well, now you're not just linked to your neighbors, right? You're also linked to your parents and to your potential children, and you can have different kinds of relationships. Maybe you don't have any relationship at all. You can traverse these node trees in different ways. This is a binary tree, and then left, right sibling representation of a tree. And so this is, a little bit more intelligent of a tree that you can traverse a little bit faster. It takes a little bit more space, of course, to do that, and a little bit more time to update all those relationships every time you update one. So those are factors. But in the tree that I've built for the knowledge node system, not the knowledge node, but the PEGN node, sorry, is represented in the, here we go. So you look at the long form of the AST, the abstract syntax tree. The abstract syntax tree is a rooted node tree. And here you go. So you have the top level being grammar, and then it has children. There's only two types of nodes in my tree. You either have parents or terminals. Terminal is something that has a value. So a major version here would be a terminal because it has a value instead of a child, or one or more children. And then you have this relationship. And as soon as you get a relationship like this, you can then do all kinds of really amazing, fancy, fun stuff, which we're going to do later, by walking or traversing or visiting all the nodes in the tree. And there's lots of ways to do that. But this is how compilers work. This is how, syntax checkers, a lot of them work and stuff. Yay, how's it going? And so that's that. This is what a node tree looks like. All right. So by the way, this is the node tree representation of the grammar here. This grammar. So and the grammar itself is telling you how to define that tree relationship. So it's like a chicken and egg thing. But this is a rooted node tree, and we're now going to model this, and I'm going to show you how to create such a structure for yourself. There's not, this kind of thing doesn't exist automatically. I'm sure there's probably something in the standard library, but making one is not too hard. I'm making a rooted node tree. So here we have this. We have this rooted node tree here. And this is an exact model of what I'm building. The only difference is that we're also going to have a reverse reference to the left side child. So if you were to take any node in this thing, if you were to take this node here, it has no idea that it has anything over here to its left, but it knows about its sibling to the right. So what you have to do is you have to create a data structure that has these relationships. And the way that looks is you have, so here's the basics of it. So you start out with a node, and this is a struct, and then we have a type, which we'll come back to later. And the types, by the way, are represented. You saw them in the other tree here. So these are the names of the different types. They're represented by integers in the compact version of this, which is why I have to redo it, because the numbers are different now. And then you have the value. So the value would only be for terminals, and as I mentioned, here we have the value is right here. We have like an alpha or a 0, and that's the actual value. But parents don't have values, right? They just have links, and that the links are not to all their children. And this is a little bit misleading when I first started this, and then I did some research. I was like, oh, okay. So they actually, you don't even need the last child. Child n is the last child. Child 1 is the first child. The only reference you need is really to the first child, because once you get the first child, as you look in the tree, you can go ahead and traverse the tree from the first child and do that with a function, which I'm going to show you here in a second. You can just do that traversing by just following the links to the next child. And that's really important, because at any moment, any one of these nodes can change its position in the tree by just manipulating itself and its immediate siblings and its immediate relations. And that's very, very powerful. That means you can move it around in any way you want. You can make it the new parent of this guy, right? Just by changing values of the things involved. And that is, that's how we deal with rather complex relationships. So anyway, for the sake of convenience, though, I've gone ahead and added a child n. And the reason for that is because most of the time when we're dealing with a node, I want to add another node onto the end of that node. And in order to do that, you need to know the last one. Now, it would be too much energy to go find the last one and walk through all of his siblings every time. So I go ahead and keep up one extra relationship, which is the last one. And then when I'm appending, all I need to do is add it to this one, so I know how to do that, and we'll do some of that in test code eventually. I don't know how much time I'm going to have to go through all this today. I do have a session starting up in an hour, but I'll go as long as I can. So I'm going to be porting over a completed and tested node tree that is over here. But as I do it, I just kind of want to talk about it while I do it. So I want to give a little bit of background first. This is in let's see. PEGN -go-first one file, and we're going to go look for, so here's, oopsie, that's not the right one. Are we in one file? Maybe I need to go do this one. I can't remember. I'll go find it. It's old PEGN. Yeah, this is Go. And so then we're going to do some node here, and so here we go. They have all of these extra functions. The truth is that you don't really need these. You could actually do all of these changes just directly, but we're not going to do that. Let's go ahead and start. So here's the children one. We need that one. We have is terminal. Terminals. I mean, this is fine. I just think that's kind of an extra unnecessary thing to do to look it up. rwxrob.live if you want to read my FAQ about everything. And then we have isChild here, and then we have isParent here, append child, last child, add op from. So actually, I'm just going to grab most of these using VI. I'm using just a search, and I'm going to grab all the way to the end, and I'm going to go ahead and put them in and do some testing. And in the process, we can uncover what's still needed and what's not. So let's go ahead and port over some of this stuff here. There is going to be, I'm going to go ahead and save this. Yeah, there we go. Had it in the previous SIB. So I'm going to have to do some name changes here right away. So we have the parent, previous sibling, and I changed previous SIB to previous. So I'm going to go search for all of those previous SIB, and I'm going to change all of those with previous. Actually, and most of the time I can just remember, I can just delete. It depends on what you're asking. He meant, shoot, and there might be somebody who can answer your question. So let's just do a 3x to delete those. I'll do that one, that one. Now I'm going to do them all individually because I'm too scared of doing it because there might be a word SIB that would not match. Just a little bit of extra effort to check them all out. But all of these methods are just maintaining that relationship as we go through. Say, CI/CD. Well, first of all, I don't have to explain CI/CD to 5-year-olds. They generally can't speak well enough to understand CI/CD. Yeah, CI/CD is just not having to deploy something because it's already getting deployed all the time. That's pretty much it, including all the testing and integration. It's just automating deployment, so you don't have to go through a development and deployment cycle like most old school corporations have done for years. That's the biggest takeaway there. All right, so I also have to change first child. Let's go ahead and change that. First child should be changing to child n, child one. And these are changes that I made, some time ago. So I just need to update that. You can get a sense of it. So the children function here is kind of a good one. This one shows you what it does. It just traverses. It just says, hey, give me the next one, give me the next one. And if it's a nil, it just stops. Yeah, I'm just kind of cleaning some of the API up. And let's see. And then we have last child. Last child can change to, what is it? Child n, I think. Child n. Child n. So here we go. I guess that. So there we go. And we've got our stuff almost done. We got nodes is undefined. We don't need a nodes, so that needs to go away. Whatever that is, that's left over from the other one. Yeah, in fact, this whole thing needs to change. This is what is unmarshalling. This is what takes a JSON string and turns it into, or byte string, byte slice, and turns it into a node tree. And that's all well and good, except for the dependency on something with nodes in it. So if there is a nodes, go ahead and do pretty. And I don't know if we want to do that. Actually, we don't need that at all. Node string. Oh, this is how we're printing it out. Yeah, we'll get rid of that. We're not going to be doing pretty printing. So the string fills the string interface. It checks to see if the nodes. Nope. I gotta clean this one out. We're gonna get rid of the long form stuff because we just killed long form. And in fact, pretty. We're gonna delete pretty. We don't have pretty at all. This will come back. It's just not gonna be for right now. And this is, yeah, to pretty print it. We don't, well, let's see. Node types. Tell you what, I'll leave pretty there and put a thing to fix it. The tough part about this is they're going to have an external dependency, and that's fine, I suppose. I just didn't want to do that. Yeah, I mean, I don't want to build an external dependency on this, but we'll see. Yeah, this might have to change. Drop the dependency on nodes. For the thing there. Now nodes was a table that looks up all the numbers to maps them to their words. That's not something we use anymore. So yeah, and that does mean that this is going to have to go away. Check test -0. Yeah, we're not going to do checks at all. That's all. This code goes away. You know what? Maybe I can do this right now. We do need to get this to work. Let's check a couple things here. So the first thing, well, JSON string can come over. JSON parsers is going to have to be considered. We have kind of a dependency critical path thing going on, and I don't necessarily want to pull those in. I'm gonna have to work on them right away though. So, but let's just look at the whole thing, and we'll drop pretty right now. Pretty's not being used, so that the JSON parser, JSON string need. So yeah, let's just drop all the stringer interface stuff for now, and we'll come back to it later. What is this? Marshall JSON. Yeah, all the marshalling will just go. So we have our node tree. The marshalling stuff is only needed for the representations of the node tree as a string, and that's really going to be important later for our error messages and stuff. But for right now, we just have to ensure that the node relationships are working. And I do have test code for that, which I'm going to pull in right now. Make sure that the test code is working. And this will help you understand what that is. Let's not go. All right, so this is, I think it's almost all been commented out. Yeah, here we go. So example node new ref. We are. Yeah, this could be tricky to do. Without our output being in words. So yeah, I mean right now it's just using integers, and we're not doing any parsing of the notation. We actually should do this in a way that that updates the output. By default, the node tree does not know what things are in it, and I'm actually kind of just hesitating because the last way I fixed this, we actually gave the node a reference to its node types, which is all it needs to know. But in order to do this, we'd have to kind of we'd have to give it something somehow. We'd have to give it some sort of name. And I'm trying to consider the best way to do that. I don't want to give every node struct knowledge of all of its types. That's like, it's just a pointer. It doesn't seem like that's needed. But to tell you the truth, that is the only thing that's required to make this 100% independent. It is just a pointer, so maybe that's worth considering again. It is relatively easy to add. It does keep the node tree very, flexible, and when it does allow the type of the nodes the names of the nodes to be defined, as opposed to being hard coded into some sort of environment for the package. So I'm going to go ahead and put types, and I'm going to put just to get it working. I'm going to say, okay, here is a actually this is a what kind of types do we have, and so yeah, this is going to be a reference to the structure. So that would be we kind of need both actually. We need the node types, and that would be like the number that goes. What does the number go with, right? And we also need what does what string, what number goes with what string, so we can do the opposite. And so that would need to be a struct of some kind. So let's go ahead and do that. This, I'm kind of playing with this. So in this case, let's say we have, we could say type PEGN, we say node types, and that would be a part of nodes, right? So, and that would be a struct, and under node types we could have the node types values, or we could say, and then we would have the numbers. It would be a map. We have a map string. Wait. Yeah, we have a map string interface. Whoops. What am I doing? We have a map string. No, string. What am I talking about? We have a map string integer. And that actually we don't, it almost doesn't even need to be an integer. It could be, nah, we can keep it an integer. And we'll put it in int. And let's see, node types, let's say by string. Let's say that would be like by ident, right? And then we would have by int would be just a map. No, just and an integer, I mean an array, a slice of strings that would match the number directly. And so yeah, yeah, that's all we really need there. I think the important thing here is that this is going to be able to be passed. This is going to be a pointer that's going to be passed to everything. So we'll go ahead and set this. We haven't had something like this before in the past. It's been close, but not nearly as good as this. So we'll have this be a reference to a node types, and that way stuff can get looked up pretty quickly. And let's kind of go down here and whoops, let's go look at this guy here. So yeah, and the reason I was doing this is because all these are going to all break. So let's go back down here and let's go see if we can fix some of this marshalling stuff. JSON string, a PEGN JSON string, that is, we got to bring that in before we bring this one back. So let's do that. I'm going to be copying temp old to, I think there's a JSON.go, copy that here. And that's got JSON string in it, which stays as is. This also has, this has to be taken off here because this can be related to there's a printable string for a token and Unicode character. Yeah. The JSON parser. So PEGN JSON parser implements the parser for a JSON string to a PEGN node. So yeah, I think we need to say I don't know. We kind of need we need like a node. We need like a parse function or something. We should probably do node from JSON or node.onMarshal. I definitely need to change JSON parser though because I don't want it to be. It's a parsing of a JSON string to a PEGN node. Init next peak parse types parse. So this is what gives you get a node parse the byte array into a PEGN node. Parse that node. Oh yeah, because you have to parse. Yeah, you have to pass in the node that you want it to parse into. I suppose we can leave it. I kind of want to leave it. So I don't know. I guess we can leave it. These kind of things we're gonna have to get rid of though. Yeah, I don't. I'm trying to decide whether we want to have a JSON parser. I think we probably don't actually. I think we probably want to make that private. And the reason for that is because all this stuff's can be private, so that's fine. These are not going to be private, however. Yeah. I gotta figure out how we're gonna handle this. I don't really want anybody to use the JSON parser directly from this package. That's not what this package is for. So some good work there from Greg doing this parser. And yeah, I'm not escaped here. See, yeah. This is a tough decision for me because this is not required, but could be useful to somebody. Frankly, it's such a small amount of code. Somebody could add it to their own if they wanted to go get it. I'm going to go grab a little bit more coffee. I'll be right back in a second. All right. Looks like I'm going to be converting some stuff to private. Just cause. So yeah, I may just do them all at the same time. And that's it? Really? Wow. Well, let's do this node. Node.go. The hard part about this is all this code is going to have to be included in the one-liner. So I don't know how that's going to go down. We'll have to look at that. Yeah. Grep ball, JSON string. That's it. All right, and then JSON parser is gonna have to change too. Actually, I'm gonna change this to be yeah. I don't think Golang JSON. I don't think Go does. I think it does all caps for that stuff. Get JSON parser lowercase. Yeah, no. I guess I need to see the Golang encoding JSON library. This is based on that. Go look at this. I just want to look at the underlying stuff. Yeah, HTML escape. Yeah, when they always use all caps when they do. Okay, good. All right, so let's first of all make that change and get that in line. All right, and then we're gonna have to make another change, unfortunately. Parser. Put an underscore in there. This is just making it so it doesn't show up as public in the documentation and everything. It doesn't change anything else. I mean, it's great code. Appreciate the contribution. But I really don't want it to confuse the package users. And it would if we didn't have that. So, all right, and these are the this is invisible. That's fine, but these are not. So these need to have underscores in front of them, and that's gonna blow up a bunch of stuff. Yeah. So find type and type. Was it line 66? That's interesting. He's mapping runes. Okay, well, I made that easy. All right, so I'm 133. Gonna go there. We got a few things to replace here. And ouch. There's a fly. These little gnats, we have these gnats in North Carolina. They suck. I hate them. They're so annoying. They are really annoying. And that one should go away. And there we go. Is that? Yep. Left bracket. What part of North Carolina? The sort of the Charlotte area, outside of Charlotte, up north. Yeah, we're kind of in the Lake Norman area, if you know where that is. Do you know that? It's Trump land. Yep, this is definitely Trump land. Fayetteville. Oh, wow. Yeah, interesting. Yeah, what do you think of all that unrest? That's pretty interesting, huh? In little Fayetteville. I mean, it's just a weird place to congregate. Yeah, it's crazy. It's crazy here. I mean, it's good stuff and bad stuff, just like everywhere. But, let's see. P string. Oops. We need to do the comment. Wait, there's still one left, apparently. Yeah. Well, there's so many tiny little areas. Stanley, we were going to go get a house out in Stanley, and I was like, I cannot live there, man. Plus, we have an Asian son, stepson. And you do not know what racism is until you've lived with... I mean, I certainly don't know, right? I'm an old white dude. But yeah, the stories my wife has about raising a Chinese son in some of the places that she's lived are just terrifying. It's insane. The racism is alive and well. Let's put it that way. 2020. I mean, why? It's just crazy. I don't want to talk about it. Let's talk about something else. Talk about something happy. Happy thoughts, right, Mac? If he's here, he's always telling me to stay happy. I'm like, okay. Oh crap! I can learn how to type. This is the kind of stuff I can do and type at the same time usually because it's like so brain dead and just yes, I could copy and replace it all, but Spain. Well, Spain is fun. I've been wanting to move to Spain too. My problem is I want to live everywhere. I'm a very much an explorer, dude. I lived all over back and learned Russian and stuff. Yeah, I very much miss being able to go all over the place. But it's not the time for that. That's for damn sure. Hey, look, our parser seems to work. So that's good news. Now we just need to fix up some of this other stuff down here with the stringer. I think it's all commented out, actually. Is it? Did I leave it commented out? Nope. Okay. Let's see. Where's our pretty? Huh. Oh, it's in the node thing. That's right. So node.go. Here's our pretty. This should actually work now. So I'm going to start play with this. This one is going to break, but that's okay. So wait a sec here. Let me think. One of these, if it has pretty, we wanted to visit. We're going to do visit. So visit and visit async. These are ways of walking through the node tree. So if you remember back to our node tree thing, we have this, you start here and say, okay, I want to go to the first child. Go here. Now, does this child have any children? Yes. Go to its first sibling. Okay. Does it have any children? No. Do its next child, its next sibling. Okay. Go here. Does it have any children? Yes. Go down and do it. Does it have any more? No. Okay. Go back up. Go back up there. Does this one have any children or peer? Yes. Go over here and then do the question. So you end up walking all the way through the node tree, and then you go back here and then back up, and then here and here and then back up, so that everything gets visited. And I have a lot to still understand about traveling salesman problem, all kinds of things that are related to graph theory. But a lot of it doesn't really matter to me, because I just need to do top-down descent first, sort of traversal. Anyway, go back to doing that. So, we have this, Marshall is in the house. Marshall JSON is not hard, because this is always going to produce an AST. That is the compact form. Print and string do the other one. So this is the one that's going to get interesting. So let's say this. If we say, if error does not equal nil, this line actually had something else in it, and I got rid of it. I want to go look at it really quick. There we go. Where's the pretty printer? Pretty, there we go. So, oh, it isn't string, okay. So that's not there. That is down here. So if we have a node types is not equal to nil, then we want to pretty print it. And yeah. All right. So undefined JSON parser. Let's go ahead and fix that now. It's going to be underscore JSON parser. And so yeah, that should work. If this works, we should get everything working actually. Marshall JSON gives us the JSON. That should be acceptable. Fulfills the stringer interface. Print. These are all public now, so I have to document them. Eventually I'm going to have to do all of that. 302, what do we got? So this guy can stay the same, and we're going to do indent. We're going to do node types and dot type. Actually, node types dot by int. Did I have by integer? What do I call it? I can't remember. By int, yeah. All right, so by int, and down here we're going to have, oh, wow. Yeah, this is interesting. Yeah, we're not going to have this anymore. We don't need that. They'll all be positive at this point. So yeah, it's actually not a node type. It's going to be a definition type, but this is kind of a generic node tree. So yeah, pretty depth into JSON. I guess I could almost make that public. If somebody wanted to have a different indentation. I mean, it doesn't hurt to make it that public. It's not gonna, nobody's gonna die. Let's see. Depth. Oh, it's talking about, yeah, what depth to start with. Yeah. I mean, I don't know. We could try that out. Non-declaration statement 297. 90. Oh, right. Oh, we're that done, I guess. All right. So this is a rooted node tree. I'm spending a lot of time on the JSON formatting for the thing, so I can actually show some testing of it. Node types is undefined. Node has no field or method. Node types. Oh, right. Types. We'll say that. Types by int, and then we pass that. So now we can do some other testing on it. And actually, all of the original tests should pass now that I've reincorporated the node testing. They're declared but not used. Did not print it? Oh. They're not print. Pass. Huzzah. And this is how you would use a node tree. So I'm just building up little ones as we go. We set a value, so this is a terminal. We could also do this. We could say, hey, println foo.is terminal should be true. Does that pass? Yep. Okay. And what? I'm actually curious on this one. I want to see which one this one is. Is terminal, is parent. Undefined foo. Whoops. Zer. So zer is false. It is not a parent, and it is a terminal, but it's got a 0 value. Interesting. Okay. That's just reminding myself how I coded it. And go ahead and test that one. We're like on time. All right. Let's see. So what we got? Let's go do some untesting. I'm almost done with this whole node tree thing. I can call it a day, or call it at least for this. Children. So the children are going to find. Now this is printing without any. So it's printing the compact version because it's not. It doesn't have a node type tree of any kind. So here we go. We make one node, and then we give a child, and then we give the child a value, and then we append that child, and then we go ahead and print it. So this shows that we've got a thing, and we can see that it's a parent. So yeah. So yeah, we can actually just do that. So let's do is print. Oops, we'll do this. We'll do print is parent. And not foo, but some. And it should be true. And okay, so here we're going to append a child, and this is a much bigger way of doing this. And we're going to stick with. I'm not going to use any fancy types here. And I do have to change some of these names. So first of all, we're going to create some constants for the types. The truth is, this is all going to change because I just changed it. And yeah, and we need to do this. We need to do type equals mum dot types equals, right? And we're going to have to say types here. So we're going to need to set some types. And I mean, this is kind of a lot to code right now. Let's do one thing at a time. So I have to update all these names here. So first of all, first child needs to change. This needs to change to child 1. Everywhere actually. Let's keep doing that. Oops. Last child everywhere it occurs needs to change to child n. I can do this with one command, but again, I like to see it. I just do. It just makes me feel better. So, and then what do we got? We got pen child stays the same. I think we have next sib too. So anything with sib in it, we can kill those 3 letters anywhere they exist. And we'll get ourselves a good test here. And yeah, so go back down. Okay, so let's actually, we have to build a little bit more of a complex structure here. Undefined types. All right, well, let's do that. So we can say that types is a, what is types? Types is a struct called a node types. And the first part of the struct is by string. And so we're going to have a thing of that. And it's going to be a map string interface. I think we can get away with just defining it. Let's go ahead and see. Maybe not. I'm going to have to do, well, map string int, I think. Yeah, map string int, and then we're going to define that. And then here we're going to have by int. And int is an array of strings. And we'll define that. And so what do we have here? So the int is going to be undef colon what? Unknown or undefined? Undef mum kid by int we just have undef wait, we have undef comma oops, did I get that right? String int. Oh no, yeah, these are supposed to be, wait, do we have all 3 of them? I guess we do. I didn't want all 3 of them. It's kind of wasteful, but oh well. This, again, this printing stuff doesn't happen in high performance capacity. So it's just for when we're printing stuff. So yeah, that can probably stand as is. I think we kind of need, this is by int. And this is by string. Yeah, we don't need this. I mean, no, right here we need, actually the way this is reversed. Yeah, I have to go look at the code. We might have to change that code. And this should be these constants. And the only reason for that is so that it can look stuff up. And this is now, we have to do PEGN Node types. I cannot use PEGN as type PEGN, so we have to take a reference to it. There we go. And then we get errors, which is fine. append child. So those are given. That's what we want. We want errors. So yeah, I can kind of tell where they are. They're in the. I'm pretty sure they're in the JSON thing, because we just messed with that segmentation fault. I need an uploader reference on what? Well, let's see. Yeah, Pretty had trouble. Pretty had trouble where? Where did Pretty have trouble? Pretty 268. All right. Node 268. Pretty depth. I wonder if children didn't work. Huh. It might be that it didn't add it. We'll have to use some of the. We're gonna have to test some of the other stuff that's not as. Yeah. Let me try something here. Get rid of these. I want to get back to the number to numeric based types. Yeah. So type equals, well, I can just do this. That passed. Okay, well, that's good. That means that all the types work. That means the pretty stuff's got a problem, which that means I'll have to come back and fix that. I don't know if I'm going to do it in this exact spot. I did change. I think I changed all of the tests to use the AST and not depend on the pretty stuff. And I suppose that's fine for now. In fact, I don't want to get rid of that though, because that was nice to have. Let's see. Let's put this down at the bottom. We might be able to use it later. All right, where are we? We've got, so append child is good. Adopt from. Guessing this is going to work too. Yep. And so this is how we do it. So we have, make a mum, give it a type, and then append the child and check all the values. So this is building node trees by hand. Of course, we're going to do that automatically in our parser, in our node parser. Yep, insert self, that works. These are all using integer comparisons, which is good. And actually, I'm going to just keep using these. I think these are, just checking one at a time. And let's do this down here. That guy's good. Yeah, I think our node tree is a solid. This is really good. I'm really glad this is up and running. What else we have? Explain node self middle. So these are all really exhaustive tests of putting nodes in different places, and so you like kind of inject the node. You can go look at this, by the way. This stuff is all up on GitLab. If you want to go read through it, if you want a good example of how to make your own rooted node tree, and you want to, this one's really interesting. So this visit, I mentioned this is how you go through it. So you make a whole bunch of nodes, build yourself a node tree, and then you make a function. You call visit and pass it a function, and it will run the function on every node in the tree in the order that I talked about earlier. And as it does so, it'll print everyone out, and that's what this does. Is it just prints everyone out. And this visiting the node tree is the big advantage over regex, because you can't do that on regex. You just have an array of matches that are flattened, and in this case, you can actually have a full tree, so you can do all kinds of stuff with the tree, and that's why we're making this thing, because we want to be able to traverse the tree to do code generation, code validation, grammar validation, compilation, that kind of thing. So that's why I did all this. Unmarshal simple. Okay, that worked fine. That's good. Okay, we're getting on to some of the trickier stuff here. So yeah, here we unmarshal JSON simple. Okay, do this unmarshal here. Oh, hey, somebody's here. Hi, I didn't hear you call. I better go. Just give me a second. I'll be right there in a second. This simple one isn't going to work though right now because it's doing the complex. I have to help unpack the car. So we're going to go ahead and call it for today. Appreciate you guys stopping by. And it looks like our node tree is finished, and I'll wrap this up, and we'll be working on probably this